So what I want to look at here is I want to look at something next called the roots test and the ratio test. And so first we want to look at this definition of absolute convergence. So the sum n equals 1 up to infinity of a sub n exhibits absolute convergence if we have that the absolute value of the sequence inside of it actually converges. And then we have that idea of conditional convergence if our sequence converges but its absolute value diverges. So what we're going to do here is we're going to make a determination about what are some tests that we can use in order to determine absolute convergence. Okay, so like let's say for example, I look at I'm what I'm going to do is I'm going to utilize this thing called the ratio test in order to do that. So we'll let the sum n equals 1 up to infinity of a sub n be a series with non-zero terms. And we'll let rho, and that's what it looks like a little p, but it's actually called rho, equal to the limit as n approaches infinity of a sub n plus 1 over a sub n. So like the n plus 1th term over a sub n. And then we have these three conditions. If rho is between 0 and 1, okay, then the series is going to converge absolutely. If rho is greater than 1 or rho equals infinity, then the series is going to diverge. And if rho is equal to 1, then we have no information. We're actually not going to get enough information. We're going to have to find some other way to determine convergence. Okay? And so basically, again, we're going to be looking at, we've got this test, all right? So we're going to want to make sure that we fulfill conditions, right? And we show that one of the three of these occurs, and preferably it'd be 1 or 2 because 3 means that we're going to have to go figure something else out. So let's use the ratio test to determine whether this series converges or diverges. So we've got the sum n equals 1 up to infinity of 2 to the n over n factorial. And what we have here is we have, we're going to take now, we're going to get 2 to the n, we're going to find the limit as n goes to infinity. And so a sub n plus 1 is going to be 2 to the n plus 1 over n plus 1 factorial divided by now a sub n, which is going to be 2 to the n over n factorial. Now, we'll have to utilize a little bit of, we'll use some work. This is going to be 2 to the n plus 1 over 2 to the n divided by n plus 1 factorial over n factorial. In absolute value, we're going to be finding that limit as n goes to infinity. And what we'll notice is that the top part is going to be 2, okay? And the bottom part is actually going to be, if you don't know this already, this is going to be n plus 1 times n factorial over n factorial. All right, so we'll cancel out the n factorials. So this is going to then be the limit as n goes to infinity of 2 over n plus 1, which equals 0. So by the ratio test, the sum n equals 1 up to infinity of 2 to the n over n factorial is absolutely convergent. Let's take a look at another example. Let's take this example, the sum of n equals 1 up to infinity of n to the n over n factorial. And so what we'll do is we will take the limit as n goes to infinity, okay, of n plus 1 over to the n plus 1 divided by n plus 1 factorial divided by n to the n over n factorial. And this is then going to be equal to n plus 1 to the n plus 1 over n to the n divided by, and again, we're going to get n plus 1 factorial divided by n plus 1, or divided by n factorial. And we're going to take the limit as n approaches infinity for that as well, right? So this is going to end up equaling limit as n approaches infinity of, and now what we're going to do, I'm going to keep this as n plus 1 to the n plus 1, okay, over n to the n. And then this is going to be divided by n plus 1, right? Because remember, that's what kind of happened the last time around, okay? And so this is then going to equal, okay, n plus 1 to the n divided by n to the n, And we want to see what's going to happen with that as the limit as n approaches infinity, right? Because we're going to just divide out 1 n plus 1, so that's going to take away one of those, okay? And so now this is the limit as n approaches infinity of n plus 1 over n to the n, and which is equal to the limit as n approaches infinity, okay, of 1 plus 1 over n to the n. And so, since rho is greater than 1, the series diverges by the ratio test. Let's look at one more. Now we got the sum n equals 1 up to infinity, negative 1 to the n times n factorial squared over 2n factorial. And so in this case, we want to know the limit as n approaches infinity, okay, and because we're taking the absolute value, we can actually pull off the negative 1 to the n's, right? Because negative, positive doesn't matter. It's going to be both. It'll be both, but we're going to do it in absolute value, so it doesn't matter. So we get now n plus 1 factorial over 2 times n plus 1 factorial. And this is squared. Okay. And we'll divide that then through by n factorial over 2n factorial. Okay. And so this is then going to equal, and I'm going to do, I'll remove the limits for just a moment. I'll bring them back in just a second. I'm just going to do some algebra. So this is going to be n plus 1 factorial. Oh, by the way, this is factorial squared over n factorial squared divided by 2 times n plus 1 factorial divided by 2n factorial. Okay? So what we have to do here is we actually kind of have to think through, so the first thing that I'm going to do here is I'm going to notice that this is basically just n plus 1 factorial times n plus 1 factorial divided by n factorial times n factorial. And so when I simplify that, that's going to end up giving me just n plus 1 times n plus 1 on the top. Okay? Now for the bottom's actually going to be 2n plus 2 factorial times 2n plus 2 factorial, 2n plus 2 factorial divided by 2n factorial. And when we simplify that, what we're going to end up getting is we've actually got 2n plus 1 and 2n plus 2 are the missing terms from 2n factorial. So this is going to end up equaling n plus 1 times n plus 1 over 2n plus 1 times 2n plus 2. So now I need to find the limit, okay, the limit as n goes to infinity, all right, of n plus 1 squared over 2n plus 1 times 2n plus 2. And if you notice, this is going to be an n squared term, and then this is going to have a 4n squared at the front, so this is going to end up being 1/4. 1/4 is less than 1, and so the series diverges. Or series converges, absolutely, by the ratio test. So that kind of tells us a little bit about how we're going to utilize the ratio test. It's actually pretty straightforward, except for the algebra. And the algebra can sometimes be a little tricky, so you want to make sure that you're practicing your algebra as you're working through the ratio test. So the next thing that we're going to be looking at here is something called the root test. And this is another test that's going to help us determine absolute convergence or divergence. Once again, we're going to have this idea of rho. But instead of actually taking a ratio between the n plus 1th term and divided by the nth term, we're actually going to take the nth root of a sub n. So sometimes this is going to work out for particular sequences, right, that are being raised to the nth power. Okay, so let's actually take a look at it. If we have that rho, by the way, is greater than or equal to 0 or less than 1, then we're going to absolute convergence. And just like inside of the ratio test, if it's greater than 1 or equal to infinity, we have divergence. So let's take a look at an example. And so we'll use this example, the sum n equals 1 up to infinity, okay, of n squared plus 3n to the nth over 4n squared plus 5 to the nth, okay? And what I'm going to notice is that both the top and the bottom are to the nth power. Both to the nth power. And so that actually indicates to me that I might want to use my root test. So I will actually go out and I'm going to find the limit as n goes to infinity, okay, of the nth root of n squared plus 3n to the n divided by 4n squared plus 5 to the n. And so it's really clean. It ends up being the limit as n approaches infinity of now n squared plus 3n divided by 4n squared plus 5, which is now just equal to 1/4. So we know that that's equal to 1/4. 1/4, that's my rho. Rho equals 1/4, which is less than 1. And so the series converges absolutely. So you can see that actually these root tests could actually be very, very nice. Same with the ratio test. A little less computation that goes into the roots test. Actually, can sometimes be a lot easier. So let's take a look at another example. We'll take the sum n equals 1 up to infinity of n to the n over the natural log of n to the n. And so to use the root test, what we're going to do is we're going to take the limit as n goes to infinity of the nth root of n to the n over the natural log of n to the n. And this ends up equaling n, or the limit, as n goes to infinity, of n over the natural log of n. Well, what we're going to get there is that that's going to end up being equal to, right, using L'Hopital's, the limit as n approaches infinity of 1 over n, which just equals the limit as n goes to infinity of n, which is infinity. So by the roots test, the series diverges. And that's the roots test. That's how the roots test works, okay? So if we have something of this form, right, where we are taking something to the nth power, we've got a fraction n over n, right, then we want to utilize that roots test, okay? And basically all you're going to do is take the limit as n goes to infinity of the nth root, right, which gets rid of the powers of n. It's really handy, really nice, okay? Now, if we look back up here and we look at the ratio test, one of the things that I want to notice about the ratio test is that I've got some value of n or power of n to the top, and on the bottom, oftentimes these factorials. So you can get rid of factorials really easily by using the ratio test as well, okay? And you can see that up here in this example as well, okay? So if you have functions of that form, all right, that's going to actually be really helpful for you in terms of determining which kind of test you're going to use. This concludes the short lecture on the roots test and the ratio test.